Hi, I'm William, and today I'll be talking about the acrobatics of BQP. And this is based on joint work with Scott Aronson and Devon Ingram. So as you can probably guess from the title, this is going to be about quantum complexity theory. And in quantum complexity theory, arguably the single most important object of study is this complexity class called BQP, which stands for bounded error quantum polynomial time, and which roughly corresponds to the set of problems that we can efficiently solve using a quantum computer. And if you know anything at all about BQP, you've almost certainly seen some version of this picture before, which roughly depicts what we know about the relationship between BQP and some of the most important complexity classes in classical complexity theory. So for example, we generally think that BQP is potentially larger than P because of problems like factoring and discrete logarithm. But nevertheless, we usually think that BQP falls short of solving the hardest problems in NP, namely the NP complete problems. And we can say a few other things about BQP. So for example, we know that BQP contains BPP, which is basically classical computation with the ability to toss coins. We also know that BQP is contained in QMA, which is sort of like a quantum analog of NP, which is in turn contained in P to the sharp P. But other than these kind of, more or less trivial containments, it's actually extremely difficult to relate BQP back to any complexity classes that we sort of care about for non-quantum reasons. So for example, we don't know whether BQP is contained famously in pH or not. And what has been extremely frustrating for those of us who work in quantum complexity theory is that by contrast, if you look at BQP's classical cousin BPP, we can say a lot more about BPP that we do not know how to prove about BQP. And just to give a couple examples, we know that BPP is contained in P/poly, which is Edelman's theorem. We know that BPP is contained in pH, the Sips-Lodman theorem, along with a couple of other results. So for example, we know that NP to the BPP is contained in BPP to the NP. So this says that if you have an NP algorithm that uses a randomized subroutine, you can sort of turn it into a different kind of algorithm where you actually choose the randomness before you choose the NP witness. And this actually can be shown to imply this next bullet point, which is that if NP is contained in BPP, then in fact the entire polynomial hierarchy is contained in BPP, which in turn implies that pH collapses. And then finally, we know that if P equals NP, well, this implies P equals BPP, which would of course imply that BPP is not equal to X by the time hierarchy theorem. And so as I mentioned, in each of these cases, these are theorems about BPP. And yet, if you replace BPP by BQP, then in each one of these cases, these all turn into open problems. And you should sort of be wondering, what is it about BPP that makes it so much better behaved than BQP? And what property of randomized algorithms are we exploiting in all of these theorems? Which is kind of arguably getting into kind of the heart of the questions that we answer in this work. Well, at least intuitively speaking, I would argue that maybe the key feature of BPP that all of these theorems kind of exploit is that anytime you have a classical randomized algorithm, so an algorithm that makes internal coin tosses, you can always, without loss of generality, view it as just a deterministic algorithm that receives as an auxiliary input a bunch of random coins, but that otherwise has no further randomness in its definition. And this is sort of in direct contrast to the case of quantum computation, where in quantum computation, randomness seems to be something that actually inherently appears at the end of the computation when amplitudes are turned into probabilities via the Born rule. And there doesn't seem to be any way that you can sort of pull the quantumness out or fix the randomness used by a quantum algorithm like we can in the classical setting. But this is all just intuition, and you should still be wondering, is there any sense in which we can actually make this rigorous or not? How can we prove that you can't pull out the quantumness like you can pull out the randomness in the classical setting? Well, unfortunately, if you know anything about complexity theory, usually the answer to these kinds of questions is, well, if you wanted to prove something unconditionally, then unfortunately we just don't know how to do that because you would first have to show that P is not equal to P space. So in other words, there are sort of limitations that, have nothing to do with the fact that we're trying to address some difference between quantum and classical computation. There's just broader questions that we don't even know how to begin to answer. And so what we complexity theorists sometimes do in these cases where we have these difficult questions that we don't know how to answer is we ask an easier question And often the easier questions we ask are these questions involving oracles. And what this means is we consider some complexity class, like BPP, for example. And we consider what happens when you augment this class with some oracle O. And all this means is that you give your algorithm or model of computation the ability to query this black box where you can feed it an input X in a single time step and get back some answer O of X. And what you can basically ask is how many queries does your algorithm need to make to this oracle in order to decide some non-trivial property of it. And of course, what makes this model interesting in the quantum setting is that we don't just get to make queries one at a time, but we can actually make queries in superposition by defining this oracle as a unitary transformation. So you can feed in a superposition of inputs and get back a superposition of outputs. And then usually what we can ask in this setting and what we might hope to prove is, for example, we might hope to prove that relative to some oracle, you can solve a problem using much fewer queries with a quantum algorithm than you can via any possible classical algorithm. And so just to give a few examples of where these oracles show up in well-known results in quantum complexity theory, well, in fact, if you look at what are arguably maybe the three most important questions about BQP, namely one, is BQP equal to BPP? Or in other words, can quantum computers be efficiently simulated by classical computers? Two, is NP contained in BQP? Or in other words, can quantum computers efficiently solve NP complete problems? And three, what is the best classical upper bound on BQP? And in particular, as I mentioned earlier, is BQP contained in pH? In each of these cases, we at least have some evidence to a negative answer to these questions in the form of some kind of oracle separation that shows that these containments do not hold. So for example, if we look at this first result, which was proved by Bernstein and Vazirani in 1992, this was arguably actually the first result we had of any kind that quantum algorithms, so namely BQP, can do something that BPP cannot efficiently. And of course, if you know anything at all about oracles and complexity theory, we know that oracles are an imperfect tool. So most famously in the IP versus P space separations, we know that there are results that we can show where certain complexity classes actually coincide, even though they can be separated by oracles, and in fact, even very unstructured oracles. But nevertheless, especially for some of these questions where we don't even know how to say anything, you can argue that, well, if you don't even know what the relativizing consequences are, so the consequences that hold relative to all oracles, then how could you even hope to start addressing them in the real world? And also in the quantum setting, I think people also are really interested in these oracle results because it turns out that in practice, for most of the quantum algorithms we know, they can be phrased using the language of oracles and black box algorithms. And finally, before I move on, I did want to just mention one thing, which is that out of these three kind of key results that I pointed out in literature, you might notice that there's a more than 20-year gap between these first two results, which were proved very early on in the history of quantum complexity theory, and this last result, which came much more recently. And this is sort of not a coincidence, as we will see, and it is not a coincidence in the sense that this work will rely on this result of Rosenthal of an oracle relative to which BQP is not in pH in several ways, both in the sense that we sort of use similar techniques and constructions that they do, but also in the sense that for many of our results, an oracle where BQP is not contained in pH is a formal prerequisite to the things that we prove. And I think with that, that's all the background that I wanted to cover, and I'm going to start talking about some of the what are the things that we actually prove in this work. And if I had to summarize this work in one slide, what we can basically show is that in the relativized oracle world, we can sort of completely unshackle BQP from classical complexity classes around it, sort of highlighting this fundamental difference between quantum algorithms and classical algorithms, where in the quantum setting, there does not seem to be a way to fix the randomness or quantumness used by the algorithm like there is in the classical setting. So what do I mean by this? Well, if you look on the right here, we have a list of results about BPP that are either folklore or well-known that essentially hold relative to all oracles. Whereas on the left, we have results that we prove in this work about BQP that sort of directly contradict these results when you replace BQP by BPP. And for many of you, I probably don't even need to explain why many of these results are interesting or even perhaps surprising. But I think I will actually try to just say a few more words, at least about one of these results, to give you kind of a flavor for some of the things that we address in this work. And this result says that we have an oracle relative to which NP to the BQP is not contained in BQP to the PH. So what's the significance of this result? Well, there's kind of this folklore result in classical complexity theory, which is actually sometimes given as like a homework exercise in undergraduate complexity classes. And it says that if NP is contained in BPP, then in fact, all of PH is contained in BPP via what is essentially a kind of a cute one-line proof where I've basically written it out, and the key step in this proof amounts to this to showing this highlighted containment that NP to the BPP is contained in BPP to the NP. And this is something I mentioned earlier, and what this basically says is that if you have a non-deterministic algorithm, an NP algorithm that uses a randomized subroutine, then you can always turn it into a different algorithm where you actually toss the random coins before you choose the NP witness. So in other words, you have some BPP to the NP algorithm. And as a result of this containment, you can show that if NP is contained in BPP, then in fact, all of PH is contained in BPP. And what was observed by Lance Fortnow in 2005 is that actually exactly the same proof goes through to show that NP in BQP implies PH in BQP if you could show this one special containment that NP to the BQP is contained in BQP to the NP. Or in other words, that you can sort of pull the quantumness out of an NP algorithm, like you could pull the randomness out. And so our result is basically an abstraction. It's a relativizing separation where this step does not hold. And so we can at least say that in the black box setting, this sort of answers this question that Fortnow raised, I guess, over 15 years ago of whether NP to the BQP is contained in BQP to the NP, because we can actually show that something even stronger relative to an oracle NP to the BQP is not even in BQP to the PH. So hopefully that gives some motivation for why this result is interesting, and hopefully you can kind of take my word for it that all of our other results are kind of fashioned in a very similar way, where we start with some well-known result about BPP or some classical complexity class. We ask whether it can be extended to the quantum setting, and then we exhibit an oracle relative to which this does not hold in the quantum setting. So I think with that, I'll move on to talking just a little bit about some of the key ideas that go into this work and some of the proof techniques that we use. And as I kind of alluded to earlier, arguably the single most important ingredient that goes into our proofs is the so-called Foralation Problem, which was introduced by Scott Aronson in 2009, and which is the following distinguishing task. So you're given a pair of Boolean functions, f and g, and you must decide which of the following holds. So either f and g are independent and both uniformly random functions, or f and g are individually uniformly random, but are chosen in some correlated fashion such that f is non-negligibly correlated with the Boolean Fourier transform of g, in which case we say that f and g are correlated. And what Aronson showed is that this problem is in BQP. And in fact, depending on how you define this problem, you can even solve this problem using just a single query to f and g on a quantum device. And Aronson conjectured and left as an open problem that this problem should not be in the polynomial hierarchy. So in other words, it should be hard for a PH algorithm to distinguish whether a pair of functions are uniformly random or correlated. And this conjecture was finally proved almost 10 years ago by Rosenthal. And this actually gave the first example of an oracle relative to which BQP is not contained in PH. So how do we use correlation? Well, arguably, kind of the key idea that goes into several of our results is to use correlation as a sort of encryption against classical algorithms, by which you can take some classical information and make that information available to quantum algorithms, but inaccessible to classical algorithms or even PH algorithms. And the idea is that you have some string of zeros and ones. And what you can do is you can turn that string of zeros and ones into a corresponding list of foralation instances, where, say, if you have a 0, you might turn that into a uniformly random pair of functions. Where if you have a 1, you turn that into a foralated pair of functions. And then a quantum algorithm, by running this algorithm that Aronson gave, can basically decode these bits. But at the same time, we know by the Rosenthal lower bound that any classical algorithm, or indeed any pH algorithm, to them, these foralated bits will essentially just look uniformly random, and hence this is, sort of indistinguishable from garbage. And what we can do with this is basically put really powerful complexity classes into BQP while keeping them separate from classical complexity classes. So this is sort of key idea 1 that goes into some of our results. Maybe the second interesting result that we prove that's kind of perhaps even independently interesting of what we use it for can be described as, you might call it like a random restriction lemma for quantum algorithms. So, so this is a structural property of quantum algorithms. And what it basically says is that if you have some quantum algorithm and you randomly fix most of its inputs to be either 0 or 1, and then leave some of its inputs unrestricted, then with high probability over this restriction, this quantum algorithm actually simplifies to a very simple function. In particular, it will be something that's basically close to, say, a low-depth classical decision tree. And if you're at all familiar with, say, circuit lower bounds, and in particular, say, AC0 lower bounds for computing the parity function, this is essentially the same technique that goes into proving those sorts of lower bounds, where you show that some complicated function under an appropriate random restriction will, with high probability, simplify to something much less complicated. And indeed, we sort of use this to conceptually prove something very similar, where, instead of an AC0 circuit computing parity, you have some like alternating layer of quantum algorithms, and you can show that even that is not able to compute parity. And finally, there's just one more kind of interesting structural property of quantum algorithms that we prove that might be independently interesting. And what this says is the following. If you have a quantum algorithm that makes T queries to its input, then there exists a classical algorithm that makes just polynomially many more queries, so something like T to the power of 5, and that approximates the acceptance probability of this quantum algorithm on a large fraction of all sufficiently sparse inputs X. So what this says, but by sufficiently sparse, we mean that if you view this input X as being divided into a bunch of blocks, then basically each block is almost all zeros, but contains like at most a single uniformly random 1 in a single location. And what's interesting about this theorem is that it bears very close resemblance to a well-known conjecture about about quantum algorithms that is sometimes called the Aronson and Binus conjecture. And the Aronson and Binus conjecture basically posits that something very similar holds, where a quantum algorithm can be simulated under a large fraction of inputs, except actually under a large fraction of all uniformly random inputs instead of all sparse inputs. So in other words, what we show, it's basically like a sparse version of the Aronson and Binus conjecture. And I guess depending on how optimistic you are, you might view this as some special case or some sort of stepping stone towards perhaps proving the full Aronson and Binus conjecture. So those are just 3 of kind of the main interesting tools that go into proving some of our results. I think with that, I'll just conclude with a few of our favorite open problems. And there are kind of 2, I guess, conceptually 2 kinds of open problems that we have. There's sort of one to qualitatively improve our results to sort of stronger oracle separations, and the other more quantitative. So I mentioned this result earlier of an oracle relative to which NP to the BQP is contained in BQP to the NP. And one very natural question that's left open is whether this could be strengthened to an oracle where NP is contained in BQP, but PH is not contained in BQP. Another sort of interesting direction to explore would be to get kind of oracle separations that are similar to what we proved, but where BQP is even more powerful. So for example, one result we had was an oracle where P equals NP, but it's not equal to BQP. And BQP is also equal to something like P to the sharp P. And there's a question of whether you can make that P to the sharp P even more powerful, say by making P not equal, or P equals NP and BQP equals X. And then finally, there's a couple of questions that are more quantitative in nature. So for example, as I mentioned, we have this simulation lemma for sparse inputs, where we can show that a quantum algorithm and all sufficiently sparse inputs can be simulated with high probability. But we sort of don't really have any reason to believe that our algorithm is quantitatively optimal, because like I said, if the quantum algorithm makes t queries, then this classical algorithm makes something like t to the power 5 queries. And the only thing we know is that essentially because of the optimality of Grover's algorithm, any algorithm of this form will need to make at least t squared queries, but it would be interesting to see if you could close that gap between 2 and 5 in the exponent. And then finally, something similar for our random restriction lemma, where quantitatively, our random restriction lemma is actually incredibly weak. Let's say if you compare it to, say, the random restriction lemmas that we have for AC0 circuits, because it basically says you need to randomly restrict all but like a square root fraction of the inputs. And it would be interesting to know if you can sort of quantitatively improve that to get something that's much closer to the, like I said, the kinds of things we can prove for AC0 circuits, where there the number of unrestricted inputs can be something much larger, like n over log n or something like that. So that about concludes everything I want to say. If you have any questions about this talk, you're more than welcome to email me, or otherwise ask me in person when I give this talk at CCC, where I look forward to seeing you. So thank you for listening.